When a robotic surgeon performs like a really delicate, life-saving heart operation, you are witnessing an absolute marvel of modern medicine.
Oh, absolutely.
I mean, you see this multi-million-dollar machine making these sub-millimeter incisions with perfect, effortless fluidity, and it's incredibly easy to assume that all that precision comes from the software.
Right, or the digital sensors.
Exactly, the computer brain. But that smooth, flawless motion doesn't actually originate in the code. It comes from a hidden, entirely unglamorous piece of threaded steel deep inside the robotic arm.
Which is wild to think about.
It really is, because if that piece of metal isn't cut with uncompromising perfection, the robot stutters, the arm misses its mark, and, well, the surgery fails. So today, we are looking at the foundational mechanics that make modern automation possible for you and everyone else.
Yeah, the stakes in high-precision manufacturing are just incredibly grounded in physical reality. We're talking about a world where microscopic machining errors, they multiply into rejected parts, severe financial losses, and just overall mechanical instability.
Yeah.
You can't simply program a machine to be smooth if the physical components driving it are inherently flawed.
Which brings us to our mission for today's deep dive. We have this highly technical engineering breakdown in front of us, and the title alone gives you an immediate sense of the hyper-specific manufacturing world we are entering. It's called How to Choose Between External and Internal Whirling Machine.
A very literal title.
Right, very straight to the point. But our goal today is to extract the aha moments from this dense text and understand how a seemingly niche choice, literally the method a factory chooses to cut a screw thread, dictates the precision, speed, and reliability of the technology you and I rely on every single day.
Because the core theme of our source material is that choosing between these two machining methods, it isn't just a matter of factory preference or budget. Choosing the wrong whirling method basically guarantees poor accuracy, unstable cutting dynamics, massive wasted costs, and delayed delivery.
It's a domino effect.
Exactly. It is a strict physical negotiation between the geometry you need and the space you actually have.
Okay, let's unpack this. We need to start with the ultimate quest in manufacturing, which is creating a flawlessly precise thread. The text identifies the gold standard for this as something called internal whirling.
Right, the gold standard.
But to grasp why it's the gold standard, we have to visualize what is actually happening to the metal here. We are talking about manufacturing a ball screw. And this isn't the kind of screw you use to build a deck in your backyard.
No, definitely not.
It's this long, slender steel rod with a deep, spiraling groove carved into it, designed to translate rotational motion from a motor into linear motion for a machine.
And the traditional way most people, imagine metal being cut on a lathe involves a tool approaching from just one side. The steel rod spins rapidly, and a single hardened cutting blade presses against the side of the metal, slowly carving away the material to form that groove.
But doing that to a long, thin steel rod creates an immediate physical problem. I mean, imagine you were trying to carve a carrot by pushing a sharp knife heavily against just one side of it.
It's going to bend.
Right. The carrot doesn't just sit there, it bends away from the knife. It flexes under the pressure. And in manufacturing, flexing is the absolute enemy of precision.
Oh, 100%.
If the metal bows even a fraction of a millimeter while being cut, the groove is entirely ruined. So internal whirling changes the geometry of that cut completely. Instead of one tool pressing from a single side, imagine a ring of peelers entirely surrounding that carrot, gently and simultaneously shaving it from all sides at once as the carrot passes straight through the center of the ring. That is internal whirling.
What's fascinating here is the physics of that hug, as you might visualize it. In an internal whirling machine, the workpiece, the steel rod itself, physically passes directly through the spindle bore or the cutter head bore.
Right through the middle.
Exactly. And the cutting tools are arranged on the inner circumference of that rotating cutter head. The source text emphasizes that this setup creates a remarkably large envelope angle.
Meaning the cutting blades are making contact over a much wider arc of metal at the exact same time.
Precisely. By positioning the blades all around the workpiece, the cutting force becomes perfectly balanced. The force is no longer concentrated on a single side of the screw. You completely negate the bending effect.
That makes so much sense.
Yeah, balancing the force drastically reduces any bowing of the steel. It eliminates the vibrations that would normally shudder through a long rod and prevents the cutting tool from deflecting off its mathematically programmed path.
And the data the source provides for this balanced environment is just staggering. Because the cutting is so stable, Internal whirling achieves surface finishes between raw 0.4 and 0.8 micrometers.
Which is incredibly fine.
Yeah. For anyone outside of a machine shop, RAW stands for roughness average. It measures the microscopic peaks and valleys left behind on the surface of the metal after a cut. At 0.4 micrometers, those microscopic bumps are smaller than a fraction of a human hair.
Wow.
To the naked eye, the metal looks like a flawless mirror. And for pitch accuracy, the text notes it reaches GB/T197 levels 4 to 6.
Those numbers represent an exceptional manufacturing standard. GB/T is a set of national standards, and pitch accuracy refers to the exact, mathematically perfect spacing between each wrap of the thread. A level 4 accuracy means the deviation from thread to thread is, well, it's almost imperceptible.
It has to be, right?
Yeah, it matters deeply because these threads have a specific raceway profile. They aren't just grooves, they are literally miniature highways where tiny steel ball bearings continuously roll. These bearings sit between the screw and a metal nut, basically reducing friction as they travel.
I can see how that requires a mirror finish. I mean, if that raceway has microscopic bumps or the pick spacing is even slightly off, those steel ball bearings are going to scrape or stick or get crushed as they try to roll through the groove.
Exactly, because internal whirling creates such a stable, balanced raceway profile, it ensures what the text calls a very smooth dynamic preload torque.
Okay, that sounds a bit complicated.
It sounds complicated, but it simply means the resistance the motor feels as it turns the screw is perfectly consistent from end to end.
Oh, I see.
There are no microscopic tight spots causing the motor to strain and no loose spots causing it to slip. This is the exact mechanical reason why high-end CNC machine tools, factory automation equipment, and precision camera stages can glide fluidly without any stuttering. The physical perfection of that cut directly dictates the perfection of the machine's movement.
Oh, wait, I have to stop you there, though, because as I was reading this first section, I kept coming back to a very obvious question.
Sure, what is it?
If internal whirling gives us this incredible vibration-free mirror finish perfection, why does external whirling even exist? I mean, why wouldn't a factory just use the internal method for absolutely everything they make?
That's a fair question.
If internal whirling is the undeniable gold standard, why would anyone ever settle for a bronze metal process?
Well, the answer is entirely based on the unforgiving limits of physical space. Perfection, in the case of internal whirling, has a hard physical size limit.
So going back to our analogy, the carrot has to actually be small enough to fit inside the ring of peelers.
Precisely. To use internal whirling, the raw metal must physically pass through the spindle or the cutter head bore. The factory is strictly constrained by the size of the hole in the machine.
Right.
The source notes that standard internal whirling equipment usually maxes out at a diameter of about 100 millimeters. Even if a massive manufacturing plant invests in rare, custom-built internal whirling equipment, they're generally capped at around 200 millimeters. A workpiece larger than that simply cannot be physically loaded into the machine's bore.
So the structure of the machine fundamentally limits the process. If a factory gets a contract to build a massive, heavy-duty transmission shaft, internal whirling is off the table before they even turn the power on.
Exactly. And the physical constraints also apply to the angle of the thread you're trying to cut. The lead angle, which is essentially the slope or the steepness of the spiraling thread, is usually restricted to about 12 to 14 degrees in internal whirling.
Why is that?
It's a direct result of the tool envelope and the structure of the bore. If a manufacturer tries to artificially enlarge the inner bore just to squeeze in a steeper lead angle, the text warns that they risk overcutting the tooth profile. The blades will strike the metal at the wrong entry point, which instantly destroys the mathematical accuracy of the thread.
Which brings us to the external solution. If the workpiece is far too big to go through the cutter has to go around the workpiece.
That's right. In external whirling, the cutter head operates entirely from the outside. The workpiece never passes through a restrictive bore. Instead, it's clamped externally.
Oh.
It might be supported by a heavy-duty chuck at one end, a tailstock at the other, and perhaps a center rest in the middle so the massive weight of the steel doesn't cause it to sag. The cutting tools then rotate around the outer surface of the metal.
And suddenly all those physical limitations we just talked about vanish. The source points out that external whirling can handle sizes starting from 46 millimeters all the way up to massive 2,000 millimeter heavy-duty shafts.
Which is huge.
We're talking about cutting threads into solid steel columns that are 2 meters thick. Plus, the lead angles can be adjusted up to plus or minus 40 degrees. That kind of extreme angle is crucial for multi-start threads or special transmission screws with very high helix angles, which you might see in heavy industrial presses or shipping equipment.
But the crucial trade-off is that you completely sacrifice the perfection of the balanced hug. Because the cutter head works from the outside, often utilizing fewer contact points at any given millisecond, the cutting force is no longer perfectly balanced. The force becomes eccentric. It fluctuates.
So you are forced back to pushing the knife against one side of the carrot. The bending problem returns.
Exactly, the bending returns.
Yeah.
With that eccentric force, the risk of vibration goes up exponentially. Tool overhang, weak support points along a massive 2-meter shaft, or just the sheer length of the workpiece can amplify those vibrations into deep chatter marks. As a result, the surface finish quality drops significantly. Instead of that ultra-smooth raw 0.4 to 0.8, external whirling generally yields an interval of 0.8 to 1.6 micrometers. The overall accuracy drops to a level 7 or lower. Manufacturers face a much higher risk of vibration marks, tool deflection, and even microscopic tearing of the tooth profile itself.
It seems like external whirling is sort of the heavy-duty hero of the manufacturing world. But it is definitely not the surgeon's scalpel. It gets the massive industrial-scale jobs done, but it leaves some scars behind on the metal.
Yeah, and for ordinary mechanical movement, lifting heavy loads or rough machining, those slight vibration marks are entirely acceptable. The machinery will function perfectly well. But if you were to use that same external process for a precision ball screw, that eccentric cutting force would create periodic feed fluctuations and cumulative pitch errors. Over the length of a long thread, those tiny inconsistencies add up until the thread spacing is completely out of tolerance.
So we have navigated the geometry problem, and we've explored the physical size limits that force manufacturers to choose one method over the other. But as we keep moving through this engineering breakdown, it becomes incredibly clear that in real-world manufacturing, the physical shape of the metal is only half the battle.
Oh, absolutely.
Factories are actually fighting two invisible enemies on the floor every single day, and that's time and temperature.
Thermodynamics in machining are frequently the silent killers of precision. A machine shop can have the perfect geometry, the most rigid machine, and the highest quality steel. But if they cannot control the heat generated by the cutting process, their accuracy vanishes into thin air.
Here's where it gets really interesting. The text brings up traditional thread grinding as a point of comparison to whirling. Grinding is an older process that relies entirely on high-speed friction. It essentially uses an abrasive wheel to, well, rub the metal away into the shape of the thread.
And friction on a microscopic level generates immense concentrated amounts of heat.
Right. Think about thermal expansion like a wooden door in your house. During the hot, humid summer, the wood swells and the door gets perfectly stuck in its frame. In the cold winter, the wood shrinks and the door swings freely.
It's a great analogy.
Heat causes materials to swell, and steel is no exception. In metalworking, if your steel rod heats up from the friction of a grinding tool, it will microscopically expand while you are trying to measure and cut it. You end up carving the thread into swollen metal.
Which is a disaster for precision.
Exactly. When the process finishes and the metal finally cools and shrinks back down to room temperature, your measurements are completely warped. The source explicitly mentions that with traditional grinding, in serious cases, you get surface burns or local softening. The heat actually tempers the steel incorrectly, permanently damaging the hardness and the lifespan of the screw raceway.
If we connect this to the bigger picture, this thermal reality is where whirling, specifically internal whirling, provides a massive technological leap over traditional grinding. Whirling is fundamentally a cutting process, not a friction process. The blades slice cleanly into the metal and shear off physical chips.
But wait, the text notes that whirling is moving incredibly fast. Shouldn't a faster cutting process generate even more heat than slow grinding?
You would logically assume so, yeah. But the physics of shearing work differently. The blades are slicing and removing those metal chips so rapidly that the heat generated by the cut actually transfers into the chips themselves.
Oh, wow.
Yeah, the chips are thrown out of the machine, carrying the vast majority of the cutting heat away with them, before that heat ever has a chance to soak into the main steel rod. The temperature rise of the workpiece remains remarkably low. You avoid that severe thermal deformation. This is absolutely critical when machining a long lead screw, because if the temperature fluctuates along the length of the 3-foot rod, the pitch accuracy from one end to the other will be entirely inconsistent.
So it essentially uses the waste material as a heat sink.
Precisely.
It keeps the metal cool, which keeps the measurements perfectly true. And because the factory is no longer forced to rely on slow, heat-generating friction to protect the metal, the efficiency gains are staggering. The text notes that whirling can be several times faster than slow turning or complex grinding.
In some cases, much faster.
Right. In some advanced applications, it is more than 10 times faster. A factory is simultaneously achieving higher microscopic precision while cutting their production time by an entire order of magnitude. The source even points out that internal whirling allows for hard cutting directly on hardened lead screws, provided the machine's rigidity is high enough to handle the force.
To achieve that level of efficiency and precision, however, the manufacturer has to look extremely closely at the tooling itself. The source makes a very important, highly technical distinction about the type of tools used inside these rotating cutter heads. A factory cannot just clamp basic, conventional welded carbide inserts into the machine and expect a mirror finish.
Yeah, the text mentions that if a factory tries to use a single conventional forming tool, the tool marks left on the metal become extremely coarse. It acts like too blunt of an instrument for this level of detail.
Right. A welded tool is essentially a piece of carbide brazed onto a steel shank and often ground to shape. There's inherent variability. If a manufacturer tries to use multiple conventional tools to speed up the process, but those tools aren't perfectly mathematically aligned with one another, the center line of the tooth profile won't match the installation reference.
So they fight each other.
Exactly. The entire thread becomes slightly skewed. That is precisely why the high-end manufacturing industry relies on indexable whirling tools.
I really want to break down what an indexable tool actually is because it sounds like jargon, but the concept is just genius. A conventional welded tool is like a chef manually sharpening a kitchen knife on a whetstone. Every time they sharpen it, the angle might change just a tiny fraction of a degree based on human error.
Sure.
An indexable tool is like a replaceable razor blade on a modern shaving cartridge. It snaps into a perfectly pre-measured, mechanically flawless position every single time. It completely removes the human error from the alignment.
That is an excellent way to visualize it.
Uh-huh.
Indexable tools allow for multiple high-hardness carbide-forming tools to be installed into the cutter head and instantly aligned to the exact mathematical centerline of the profile. They can finish the thread raceway in one single continuous forming process without the operator having to guess if the angles match.
Amazing.
By using indexable tools inside a perfectly balanced internal whirling ring, the machine maintains the cross-sectional shape and the pitch diameter effortlessly.
So a combination of the balanced ring and the mathematically perfect indexable blades prevents those coarse vibration marks, it prevents the microscopic tearing of the steel, and it guarantees that when a technician finally assembles that ball screw into a robotic arm, the dynamic preload torque is flawless. The motor won't struggle, and the robot won't stutter.
The choice between these engineering methods ultimately dictates the lifespan, the capability, and the financial viability of the final machine. It is a constant balancing act of managing heat, extending the life of the cutting tools, and drastically cutting down production time on the factory floor.
So what does this all mean? If you are a manufacturing engineer or just someone trying to understand how the incredible, seamless machines around us are actually built, it all comes down to a very clear division of labor dictated by the laws of physics.
Very true.
Internal whirling is the uncompromising choice for ultra-precise, balanced, and fine-finished ball screws. It provides the geometry of perfection by hugging the metal and keeping it cool. But when a factory hits the physical limits of space, when they need massive 2-meter diameters, extremely steep angles, and heavy-duty flexibility, external whirling steps in to handle the massive jobs that internal machines simply cannot swallow.
It serves as a perfect example of how engineering requires constant, unavoidable negotiation with the physical world. An engineer identifies the primary constraint, whether that happens to be the bending force of a slender rod, the thermal expansion of hot steel, or just the physical size of a borehole, and they choose the specific process that minimizes that exact variable.
I really want you to remember this concept the next time you see a piece of automated technology. Whether it is a seamlessly moving 3D printer, a high-speed assembly line, or that surgical robot operating with sub-millimeter precision, you are looking at a complex system whose effortless smoothness was fundamentally decided months or years ago by a deeply technical choice on a factory floor.
A choice of whether a piece of raw steel was threaded through a whirling ring of blades or was aggressively cut from the outside.
Right. That invisible choice, made long before the machine was ever turned on, is what makes modern automation possible.
This raises an important question, though, one that really highlights the strange, almost paradoxical nature of modern precision manufacturing. The source text focuses heavily on machine rigidity and transmission accuracy. We noted earlier that high-precision ball screws, the exact ones made by internal whirling, are the fundamental components required to build the high-precision CNC machines that actually do the manufacturing.
Oh, right. The machine needs perfect screws inside of its own arms to move its own cutting tools perfectly.
It is an endless closed loop. The precision of the tool making the screw depends entirely on the precision of the screws that were already built into it. So how do we eventually break past our current mechanical limits?
That's a trippy thought.
How do you machine the ultimate absolute perfect screw when the machine doing the cutting inherently possesses minute vibrations and microscopic errors of its own? How did we cut the first perfect screw?
That is a brilliant point to leave you with. How do you build a flawless machine using parts that were inherently made by a flawed machine? We'll leave you to ponder that puzzle. Thank you for joining us on this deep dive, and remember to keep questioning the hidden mechanics of the world around you.